All right, today is lesson 8.8. It is your last lesson of the trimester and of unit 8. This is a really tough lesson, so be patient while you're taking notes and pause and rewind if you need to, and please feel free to mark places in your notes you'd like to ask questions, because this is a pretty tricky lesson today. Your aim is that you can solve real-world problems using systems of inequalities. So the last lesson we talked about systems of inequalities, and now we're going to look at like a real-life word problem, something that might show up on the extended response portion of the Regents. Okay? So we're going to have to read really carefully and try to understand the problem. So there are many situations that arise in business and in engineering that necessitate systems of linear inequalities. The region in the xy plane that solves the systems often represents all of the viable solutions to the system. So being able to visualize this region can be extremely helpful. As always with modeling, it's important to really read the problems and understand the physical quantities involved. So we're going to read really carefully. So let's take a look at exercise 1. John mows yards. Let's scroll down a little bit. John mows yards for his father's landscaping business for $10 per hour. And he also works at a bakery for $15 per hour. He can work at most 52 hours per week during the summer. This at most 52 hours is very important. He needs to make at least $600 per week to cover his living expenses. Okay, so let's look at part A. If John works 14 hours mowing and 30 hours at the bakery, does this satisfy all of the problem's constraints? So this is one of the constraints right here in green. He can only work at most 52 hours during the summer, and the other constraint is that he needs to make at least $600 per week. Okay, so he can't work more than 52 hours, but he needs to make at least $600 a week to cover his living expenses. So if he works 14 hours mowing and 30 hours at the bakery, does this satisfy the constraints? So first of all, 14 hours mowing. 14 hours mowing. Well, how much does he make mowing? He makes $10 per hour mowing. So 14 times 10. Plus, how much does he make at the bakery? 15. So he's going to work 30 hours at the bakery, making times 15. And let's see what that equals. 14 times 10 is 140, and 30 times 15 is 450, which gives me 590. Okay, so that's how many hours he works. And now let's look at our constraints. He can only work, that's not how many hours he makes. That is how much money he makes. So he makes $590. Is that going to cover his expenses? Does he need to make, he needs to make more than 600. 590 is less than 600. So this is false. He's not going to be able to make enough money. So no, it does not satisfy his constraints. Okay? So how can we figure out how many hours he can work and still make enough money to cover his expenses? We can create systems to help us see all the different possibilities that John can do. Okay, so we're going to start off slowly and make two equations. Letter B says if x represents the hours, so x is hours, and y represents, the hours he spends mowing, and y represents the hours he spends at the bakery, let's write a system that describes this situation. So we're going to make two equations. We're going to make one equation that talks about the constraint on the hours he has to work, and another one on the constraint on the money. So your two equations talk about the constraints. He has to make at most 52 and at least 600. So the first equation, let's do the hours. I'm going to make that green because that's what I had it circled in the thing. So let's talk about the hours. This phrase, at most, right here, when you see the, and I'll scroll up a little bit so you can write this time in your notes. If you see the phrase, at most, that means he cannot work more than 52 hours. So he can't work 53, he can't work 54, he has to work less than 52. So whenever you see this phrase, at most, it's going to be a less than or equal to sign. So he has to have less than or equal to 52 hours. He can't work more than that. So I'm going to make x, the hours he mows, plus y, the hours he is at the bakery, has to be less than 52 hours. Okay, so he could work 30 hours at the bakery and 20 hours at mowing, and he'd be less than 52. So that's our first equation that satisfies the hours constraint. Okay? The second equation has to do with the money. And they tell us that, well, he wants to make at least right here, 600 per week. Well, something else to memorize, when you see the phrase at least, he can't make less than $600. If he only makes $500, he can't pay his bills. So he has to make more than, right? So this has to be a more than. And this has to be the less than. I know it's kind of weird because you think of the phrase at most and you think big, so you think greater, but it's the opposite. So this right here is something you have to memorize for these word problems. If it's an at most, you're going to use a less than sign. If it's at least, you're going to use a greater than sign. So I know for my money, I have to be greater than $600. I've got to make more, and in order to do that, I'm going to get paid 10 hours at the 10 hours at the mowing, plus 15 hours at the bakery. So 10x plus 15y has got to be greater than 600, which is how I got this equation over here, right? I did 10 times the 14, 15 times the 30. Okay, so this right here, this is our system. We've written the two equations. Writing the equations is the hardest part. It really is. It's tough to write these equations and make sense of these problems. Okay, and now letter C. If John must work a minimum of 10 hours for his father, will he be able to make enough money to cover his expenses? Okay, so if he works 10 hours for his father's mowing, so he works 10 hours mowing, plus however much he works at the bakery has to be less than or equal to 52. So let's figure out then how much he needs to work at the bakery. What's his maximum? So I'm solving this equation to figure out y. Y is going to be less than or equal to 42. So this means he can work at the bakery 42 hours and still work with his dad for 10 and meet that 52 requirement. Okay? But now we have to figure out, well, will he make enough with the $600? So let's put that into the other equation. So now it's 10. Let me use a different color here. Let me use the red. So he's going to make $10 at his dad's, at mowing his dad's lawn, so, or whatever. So that's 10 times 10, because he makes $10 and he works 10 hours. Plus, he's going to work 42 hours at the bakery, and that pays 15. And that's got to be bigger than 600. Okay, so let's see if this works out. 10 times 10 is 100. 42 times 15 is 630. And is that greater than 600? Absolutely. You're going to get 730, which is greater than 600. So this is one option he could do. He could work 10 hours with his dad and then work 42 hours at the bakery. Okay? Yes, he has enough money. So the answer to the letter C is yes. Now, we don't have enough time to really figure out all of the different combinations of hours and cost. That's a lot of work. And this is why businesses use these equations, because they want to figure out the best option without having to guess and check every time. So letter D says, graph the system of inequalities with the help of your calculator if needed on the axis below. Use the space below to think about how to graph these lines. So this is going to be a tough problem because we have this this grid that does not have any markings on it. So we have to be really, really careful about how we graph these two things, right? So the first thing I have to do is I'm going to take the green, that's x plus y is less than or equal to 52, and I'm going to solve it for y because I can't graph without y equals mx plus b. So I get y is less than or equal to negative x plus 52. Okay? Now I've got to do the same thing for the red. I'm going to have 10x plus 15y is greater than or equal to 600. Subtract the 10x. I get 15y is greater than or equal to negative 10x plus 600. And now I've got to divide both sides by 15 to get y by itself. And I end up with y is greater than or equal to negative 2 over 3x plus 40. So these are the two equations that I have to get onto my grid. Okay. Okay, so now I'm going to label my grid. I know my y-intercepts are 52 and 40, so I'm going to go up by 10s. Try and make them evenly spaced. Oops, I skipped 30. Try and make them evenly spaced out. And 50. Hours mowing, and I'm going to have to think about this in terms of his maximum hours, he can spend. So we're going to keep this the same as 10, 20. We're going to keep these the same. Okay, so keep in mind your lines might not be perfect because this grid is not, lined up. We're going to make estimates of what this might be. So let's do the green one first. The green one is going to have a y-intercept at 52, so about right here. And this slope is -1, which means it's going down 1 over 1, down 1 over 1. Another way you can think about this is that it's going like down 10 over 10. So it's going down the same amount it's going over, which makes that a nice, makes that easier to graph for us. Okay, so my graph, I know I'm also going to end at 52 over here, because if I plug in 52 into there, I get 0. So I know I'm going to have a straight line from about 50 to 50. So that's one way that I can make my line be straight. Okay, now we have to think about our shading. We're going to shade below because we have a less than. So I'm going to shade everything below this line. Okay. All right, now let's do the red one. So the red one, I have a y-intercept of 40. So I'm going to put a red dot here. I'm also going to keep in mind, if I plugged in, if I wanted to figure out where this graph intersected down here, I could put in 0 for y and figure that out as well. But I also know that the slope of -2/3 is a smaller slope than 1. So I know that it's not going to go quite at the same steepness as this other one. So I'm going to go ahead and make my line so that it's a little bit less steep than the other one. Let me redo my green here. Sorry about that. The other way I can do this is rise over run. I can go down 2 over 3, and this might take me a little bit longer to do, but it's going to give me kind of a better line. So I'm kind of going down 2 over 3, and I'm seeing that I'm going to intersect this line somewhere here. Now this is not exact. This is an estimate because I don't have points on my grid. Okay, so my line's not that great. Again, keep in mind this is just an estimate. I'm going to reshade the green to make it clear. This is still shaded below here, shaded below here. And now with the red one, this is a greater than, so I have to shade above. So now I'm going to shade above this red line, and notice that this part that's overlapping, right? This part right here that I'm going to highlight. This little triangle guy. Now keep in mind this graph is kind of an estimate because I don't have a grid. So I'm estimating this little triangle area. Okay? So let's go on to E. I've graphed both my lines and let's see what E is going to ask me. John's father needs him to work a lot at the landscaping business. Show the point on the graph that corresponds to the greatest number of hours he can work while still covering his expenses. So this is the landscaping business right here, right? This X is landscaping. So this question, oh, sorry, that was the bell. This question is asking, where can he work the most landscaping hours? Well, and still covers expenses? That would be right here. This point right here corresponds to the most landscaping hours. Now, I'm estimating that that's about 30, right? Because that is part where the green and the red are shaded in. You can't really see it that well there, but the green and the red are overlapping here. And that would be the maximum he can work while still being part of the solution. So, this point where they intersect. Now, one way to figure that out would be to put both equations equal to each other and then solve. That would be one way to do it, to figure that out. But we don't need to figure that out because the graph shows us that already, okay? So now it says algebraically find the greatest number of hours that John can work for his father and still covers expensive. So this is the part where we need to figure this out algebraically. So this point right here is where the equations are equal. So I'm going to take the green equation, and I'm going to take the part that's negative x plus 52, and I'm going to set that equal to the other red equation, negative 2x plus 40. And this will tell me where that answer is. Okay, so I'm going to solve this by adding 2/3 x to both sides. This gives me negative 1/3 x. Bring down the 52. These cancel out and I get 40. Subtract 52 on both sides. Let's extend the page here so I have a little more room. These cancel out and I have negative 1/3 x equals 40 minus 52 is negative 12. Multiply both sides by negative 3 to get rid of this denominator. And I'm left with x equals 36. So this is saying that he has to work 36 hours mowing to make $600. He'd also have to work the leftover, whatever 52 minus 36 is, to make up the hours. So this would be 16 hours at the bakery. Okay, now if you look at my graph, my estimate's off, right? This point should be maybe like way down here to get to 36, right? But again, they didn't give me plots on this graph, so this graph was kind of an estimate. But this point should be at the point 36, 16, okay? All right, moving on to the next exercise. I know this lesson's pretty long, so bear with me here as we get through this. Exercise 2, for each of the following, write a system that models the problem. You do not need to solve the system. So, exercise 2, Frank is putting together a bouquet of roses and daisies. He wants at least 1 rose, okay, I'm going to underline that, at least 1 rose and at least 2 more daisies than roses. Roses cost $4 each and daisies cost $2 each. Frank must spend $40 or less on this bouquet. So he has to spend, he can't spend more than $40. He's got to spend less than $40. If R represents roses and D represents daisies, write the system. All right. So I'm going to write this out. R equals roses and D equals daisies. Now, we've got 2 pieces of information, okay? Or actually, rather, we've got 3 pieces of information. Number 1, the first thing we know is that he must buy, oops, wait, hold on. Sorry. He must buy at least 1 rose. So we know that. Okay, so we're going to have, this is actually going to be several problems. So him buying at least 1 rose has its own equation. That one equation, I'm going to underline that with red. At least 1 rose, and let's underline this other part in blue. And at least 2 more daisies than roses. So, number 1, he has to have at least 1 rose, so roses has to be greater than or equal to 1. That's our first equation, right? He has to buy at least 1 rose. The second thing we know is the blue part. He has to buy 2 more daisies than roses. So he must buy at least 2 more daisies than roses. Okay, so how do we write that equation? Well, if he has to have 2 more daisies than roses, that means that your daisies have to be greater than or equal to R plus 2. However many roses you buy, plus 2 has to be your daisies because he wants 2 more roses than daisies. And finally, the third piece of information the system has, that's the part in green that I underlined, is that Frank must spend $40 or less. So Frank must spend $40 or less. Okay? So to write this equation, he has to spend less than $40. So I'm going to put the less than $40 right away. And now I'm going to put the cost of the roses. So roses cost $4, so I'm going to have 4R. And daisies cost $2, so I'll have plus 2D. And these are my 3 equations to my system. Remember, a system can have more than one equation to it. So these are my 3, and if I were graphing these, I would graph all 3 and find out where they intersect. Okay? Letter B. A diet food company is attempting to create a non-carb brownie composed entirely of fat and protein. The brownie must weigh at least 10 grams, but have no more than 100 calories. So, there's our information right there. It has to weigh at least 10 grams, and it has to have no more than 100 calories. Fat has 9 calories per gram, and protein has 4 calories per gram. So, let's first define our letters. So, X is the protein, and Y is the fat. So the first part says that it has to weigh at least 10 grams. Okay, that means that however many grams of fat, or protein, plus however many grams of fat has to be greater than 10, because it's got to be at least 10. Okay? Remember, this phrase at least means greater than or equal to. Okay? The second piece of information says that it can't be any more, no more than 100 calories. This is a fancy way of saying it's got to be less than or equal to 100. Right? It can't be bigger than 100. So when I write this thing, I'm going to put less than 100. And I know that I've got 9 calories per gram with fat, and protein has 4. So fat is 9, so that goes with Y. So I'm going to have 9Y plus 4X. Has to be less than 100. Okay? All right. Exercise 3. I'd like you to do as part of your fluency. So I'm going to put on here to do this as part of your fluency. I'm going to post the answer key for this soon, but I would like you to try exercise 3 for your fluency. It's very similar to exercise 1, and this is something I'd be happy to do with you in class. The only reason I'm not doing it here in the video because it will take me probably another 10 or 15 minutes to explain it, and honestly I'd rather you attempt it and and then try and talk to me in class. I think that'll be more beneficial for you. So take exercise 3 as fluency, and then come talk to me about it, and it'll be part of your mastery. Okay? Thank you for a great trimester. You guys worked really hard, and let me know if there's anything I can do to help you. Good luck.